So before the break, we have talked about how to do the estimation for the basis coefficients when we have a roughness penalty, right? And you can see the formula basically are very similar, except there's a roughness matrix are there, right? But the rest are pretty similar as when we learned the non-parametric regression. Okay, so now I'm going to show you the code how to do the estimation. So we were using a very good package in R called FDA. Um, so um, as I mentioned in the first lectures, there's a very good book called Functional Data Analysis using R and MATLAB. It gives a lot of examples and explanations about this package FDA. So if you want to know more detail about this package, I highly recommend you to read that book. Okay, so now let me show you one specific examples. How can we do the non-parametric regression and also smoothing splines using the FDA package? So firstly, you need to install this package, install the package by FDA, and then you can using this library FDA. So here, first I generate some basic functions. Here I use the B-spline basic functions. I just want to give you the ideas how to do this. You will see very simple. So the function used in FDA to generate the B-splines is the function called create.bsplines.basis. So for these functions, it requires some argument, like you need to first define the boundaries of the interval. So here, my time point is from 0 to 1. I have one data point every 0.01, equally spaced time points. And so the boundary will be 0 and 1. Okay? And then you need to give the number of basis functions. So actually the number of basis function we know is equal to the number of interior nodes plus the order. Or you can use the number of all the nodes, including the boundary, plus the order minus 2, right? Basically you can use this formula. And then you need to specify the order of the B-splines. So here I'm using cubic B-splines, so the order equal to 4. And then I specify the nodes. So here I don't want to using the roughness penalty, so I just using a less nodes. So here I put 11 nodes. So basically I have one node every 0.1. So then basically here you just need to define first the node location. So that's a kind of a sequence of points, and then you need to define the order. Okay, and then the rest, the number basis function is defined, and then you can create the B-spline just using this one line. Okay, so now let me run the code. So I created these basic functions, and then so you can, after you get these basis B-spline basic functions, then you can evaluate these basic functions at any time point. So the function used in FDA is called evaluate eval.basis, and you can specify which time point you want to evaluate, and then you give the basic function. So here I just evaluate this basic function at all the 101 time point. So now if I look at the dimension of this this basis function, basis matrix, it will be 101 times 13, because I have 101 and 13. I have 101 observations and 13 basis functions. So so each column of this basis matrix will be one basis functions. Okay, so this basis mat will be the phi in the slides. Okay, so so now if we plot the first column, okay, and so it will be the first basis functions. So this will be the first basis functions. Okay, and so then we can also plot the second basis functions. So the red one will be the second basis functions. And so now I can also plot all the basis functions. So here, each color represent each curve, with different color represent one basis functions. Okay, so you can see here for these basis functions, for example, they are all looks like a bell shape, right? Except at the boundary part. Okay, so you can see here for the middle part, all these basis function looks very similar, right? It's like it's just a horizontal shift. Okay, it's a bell curve, and it's only 90 at 4 segments, right? Yes, and so here this dash line indicate the location of the nodes. Okay, and besides these middle basis functions, if you look at these first basis functions, actually the first basis function is very special. You see, it's only 90 at the first interval, right? And also, you can see the first basis function started from 1, right? And then going to 0. And so you can see here, for any given point, for example, if you look at this point, right? If we cut this part, you will see there is a 1, 2, 3, 4. So for any given time point, there will be 4 basis functions to define the value of this. Imagine if we fit a curve. So the value of the fitted curve at this point will be defined by these 4 basis functions and their coefficients, right? Okay, and so the only special part is in the boundary. So you can see the boundaries, only the first basis function is equal to 1. All other basis functions equal to 0, right? So this is very special in the boundaries. For example, if we want one function x of t equal to 1 when t equal to 0, okay, if we have so this is actually a common constraint. So if we want x0 equal to 1, right? So what we can do? So if x of t is a linear combination of the basis function, right? And we wanted the x0 equal to 1. So in that case, we can just set the coefficient to the first basis function equal to 1, right? Then it will be, let me see. If the first basis function equal to 1, yes. I guess if first basis function, if the x0 equal to 1, we can just set the coefficients to the first basis function equal to 1. Then the x0 will be equal to 1, right? Yes. And if you want x0 to be equal to 0, you can just set the coefficient of the first basis function equal to 0. Yes. Okay. Okay, so this is the basis function. So you can also look at evaluate the second derivative of the basis functions. So for example, if you want to look at the second derivative of the basis functions, if you want to evaluate the first derivative of the basis function, you can still using the evaluate.basic function, and you can just see put 1 here. It will return the derivative of the first derivative of all the basic functions. So if you can run this, let me see. Okay, so I believe should be good. Okay, let me see what these warnings. Okay, I guess this maybe doesn't matter. Okay, so if we draw the first derivative of the basic functions, so this will be the first derivative of all the basic functions. Okay. Okay. So this is about the basic functions, and you can see it's very easy to create these B-spline basic functions. It's very easy to evaluate these basic functions and also the derivative of these basic functions. Okay. So now, if we generate a true curve, this is my true curve, and then we can put some noise on this true curve to generate the data on Y observations. Okay, so here these circles represent the observations. So now we want to estimate these curves based on the discrete noise observations. So what we can do is basically we using our formula. So phi here is the basic matter is the phi, right? So will be phi transpose. So in R, phi transpose will be T times basic matter multiplied by phi and the inverse. So using G inverse function is the inverse of this phi transpose times phi, multiply phi transpose, and then multiply by Y, right? So this will be the coefficient C hat. Okay, so this C hat will be a certain length 13 vector. So that's represent the coefficients to each basic functions. And then we can get the fitted curve. We just using the phi times the C hat, get the Y hat. Okay, so if we plot this, and so these red lines here will be the fitted curve here. Okay, and so when we look at this fitted curve, we can see generally this fitted curve is a little bit overfitting, right? It looks like less smooth than the true curve, right? Okay, so this is kind of give you the ideas. And then we can estimate the sigma square, because we know that the sigma square equal to SSE divided by n minus the number of coefficients, right? So then we can estimate the sigma square. So this is the estimation for the sigma square. So if we take the square root of sigma 2, the estimated sigma 2, SQRT, right? Okay. So let me see what's the sigma I use. So I use the variance of standard deviation 0.03, so it's pretty close, right? Yes. Okay. So after getting the sigma square, And then I can also get the variance of the fitted curve. So we're using the smooth matrix S mat, right? And so I can get the variance of y hat. So then I can get the confidence interval for the fitted curve. So I put it here. Okay, so this kind of will show you the 95% pointwise confidence interval for the fitted curve. Okay, so this is the regular splines regression. Okay, so now let we try the version when we have the penalty on the spline regression. So now we look at the smoothing splines. So for the smoothing splines, a big thing is to find out the R mat. Okay, in the formula we have the R, right? The matrix R. Okay, so for the R mat, basically it's the integral of the second derivative of the basis function times the transpose of the second derivative of the basis function. So we can use some numerical quadrature method. So what we tried one method is called composite Simpson rules. Okay. So if we Google the composite Simpson rules, basically when we estimate the integral of a function, and so we will write down this integral as a summation at certain points, and so here they define they put a weight so the boundary part will be 1, and then will be 4, 2, 4, 2, and 4 until 1 in the boundary, and multiply by the length of the partition divided by 3. Okay, so this is the Simpson rules on how to evaluate the integral of the function, and so here we're using the composite Simpson rules. Basically, we have all the number of quadrature points, and then we can using this formula to calculate the integral. Okay. Yeah. Okay. So we're using this formula. So now let's going back to our code. Okay, so now I defined the quadrature points to between 0 and 1, every 0.02. Okay, and so the number of quadrature points, let me see, is equal to 51. So it's an odd number. Okay, the number of quadrature points for Simpson rules had to be odd number, and then we can put the weight. So the weight will be 1, 4, 2, 4, 2 until 1, right? So here I kind of generated this weight based on this code, and so you can read this code more carefully after class. But here I can show you, so you can see here basically it's 1, 4, 2, 4, 2 until 4, 1, right? And then you will multiply by h delta divided by 3. Okay, so this is the quadrature weights. So after we got the quadrature weights, so first we can evaluate the second derivative of the basis function at these quadrature points. Okay, so this will be our second derivative of the basis functions, and then you can using this matrix multiplications and get the R matrix Okay, so this is the R matrix. So here the dimension of the R matrix should be 13 by 13, right? Okay. Yeah. So now we can define the giving a value for the smoothing parameter, and then we can define the B mat equal to 5 transpose times phi plus lambda times R, right? That's kind of the part inside the bracket in our formula. So the C hat will be the inverse of this B mat times phi transpose times Y, right? So this will be our C hat, okay? So C hat is a vector of the basis coefficients, okay? So length 13, and then we can look at the fitted curve by using phi times C hat, and we get a Y hat. So we can look at how close the fitted curve with the true curve. Okay, so this is so the black one is the true curve, and the red one is our estimated curve. Okay. Okay. So I guess here we can also compare the two what we get before, right? Let me put this as as Y hat 2, and just to see how the difference between these two. Okay. So this will be without the penalty term, right? Okay. So then we put this Y hat 2 to see whether we can get a little bit smoother. Okay. Actually, it's very close, right? It's so close. I see. So maybe you can try a larger lambda. Maybe this lambda is too small. See any difference? Okay, so in that case, actually it's too smooth, right? The red one is too smooth. Okay. Let me try the 0, 1. Okay, so this is a little bit different now. So the red curve is when we're using the roughness penalty, right? The blue curve is when we don't use the roughness penalty. The black curve is the true curve, and you can see here at least the red curve is a little bit smoother than the blue curve, right? Yes. Okay. And then we can look at the degree freedom. So the degree freedom will be the trace of S mat. Okay. So let's look at the degree freedom and the number of basis functions. And you can see here, although we have 13 basis functions, the degree freedom or the effective number of parameters is only 3.37. Okay. So then we can also look at the estimation for sigma square. So let's look at the estimation of sigma square. So it's also close to 0.03, right? Which is the true standard deviation of the noise. And then we can add the confidence intervals. Again, we were using this smooth matrix as mat, right? And so we can add this confidence interval on the fitted curve. Okay, so this kind of will show you how to estimate the how to do the non-parametric regression using B-splines, and how to add the roughness penalty using the second derivative to define the roughness penalty and get the doing this smoothing splines.